So in this video, I'll go over two more of the problems. Problem number 7 is a Riemann sum problem, super easy. If you know what a Riemann sum is, you just do it. It takes 3 minutes and you're done. I'm not going to go over it. Instead, I'll go over quickly problem 8. Another easy problem if you know the context. Here I've given you the first and second derivatives of a function and an unknown function. This is a problem just like what we had on, was it 2 exams ago? Exam 3. Just different derivatives. And again, there were slightly different versions. The one I'm looking at has this. In part A, find all local extreme. And well, the candidates are the values that make the derivative 0. You can write that equation out, but it should be obvious. Plus or minus 2 are the candidates. And now we need to know, like, is there really an extreme value there? We can use the first derivative test or the second. I'll do both. It's the first derivative test. I want to analyze the sign of the first derivative. You know, we've got that, the denominator is always positive. We can ignore it. And we have x squared minus 4, which of course is x plus 2. The very first kind of problem I taught you how to solve back in August, it comes into play. We have a sign change at -2 and 2. And because of the x squared is positive, the signs are going to go like this. So by the first derivative test at -2, we have a local max. The function is increasing, and once we leave -2, it starts to decrease. And therefore, at +2, we have a local min. First derivative test. Since the second derivative is sitting there, we can use it as well. In fact, it's probably easier. F double primed of 2. You can tell by looking at it, it's a positive number. It doesn't really matter what the number is. It's positive, and therefore the graph is concave up. And any extreme value on our area that's concave up, it's got to be a local min. And obviously F double primed of -2. The other critical point is negative. Concave down, therefore we have a local max. And we're done with problem 8. Lock those 10 points up. All right, finally, number 9. I wonder how many students will I not have to grade problem 9 because you chose to opt out of it. So we have a cone with fixed slant height L. And I described slant height. Here's the cone. You know, the cone has a height and a radius, but then it has this slant height, which we're going to call L. We're going to solve for all possible. We want to maximize the volume. Then we could have a short, fat cone, which that's a terrible picture. Which doesn't have a whole lot of volume. Or we could have a tall, skinny one, all with the same fixed slant height L, doesn't have a lot of volume. Somewhere in the middle, in between those extremes, is one with the maximum volume. So I told you, in case you needed to know, the volume of a cone is pi over 3 r squared h. So a lot of these problems, we get a function of 2 variables. We need to eliminate one. The easiest way to do it is just form a right triangle over here. And you can see the legs of the triangle are R and H, and the hypotenuse is L. So R and H are related by Pythagorean's theorem in exactly that fashion. Because we have an R squared in the volume, it'd be the easiest way to do it is to solve for R squared, and then we get volume purely as a function of H. R squared will be L squared minus H squared. And then we have the last h here. Let's multiply it out for easy derivatives. L squared h minus h cubed. Obviously, h cannot be negative and it cannot exceed L. And since we have a closed interval, then we're going to use method 1 for the absolute max. Excuse me, take the derivative. Pi over 3, L is a constant, so L squared minus 3h squared, set it equal to 0. And the pi over 3 goes away, and you can see h squared is going to be L squared over 3. And therefore, h is L over the square root of 3. Now, that's a critical point. It doesn't mean it's a maximum. So we need to take it one step further and make sure that there is actually a maximum there. So I'm going to use the second derivative test. And second derivative doesn't look too complicated. Here's the first derivative, so I'm going to get pi over 3 times negative 6h. Derivative of L squared is 0. That's a negative number for all positive h's. Therefore, it's concave down. Therefore, at this critical point, there is a local max. And by method 1, there is the volume at the endpoints is 0, pretty trivially. And so by method 1, it's absolute. Okay, now, to finish the problem, we go back and read it. And again, the instructions were a little bit different. The exam I'm looking at, it says find the dimensions. So here's our answer. I think at least one class asked for the volume, the maximum volume, not the dimensions. So we got h, it's L over the square root of 3. And now we need R, which we get way up here. R squared is L squared minus H squared, and therefore R is the square root of L squared minus H squared, but remember H is L over the square root of 3. So probably if you did all this, including using method 1, you could probably get full credit for that answer, but we can certainly simplify it. Let's work on it a little bit. So R is the square root of L squared minus 1/3 L squared. Well, that's 2/3 L squared. And that is the square root of 2/3 times L. So the height should be that. The radius should be that. Notice that is equal to, again, this is just for the fun of it, the square root of 2 times h. So the radius for the cone of maximum volume, the radius should be the square root of 2 times the height of the cone. All right, so that's it. It's just for, in case you're interested, having done the final. See some of you next semester. If you have any questions for me, feel free to shoot me an email. And at some point I'll respond. Again, I said this at the beginning of the first video. I've not graded a single problem on a single exam, so if you're anxiously awaiting, you have a while to wait. I don't think I'll actually be able to start grading until Wednesday of next week, so you can just relax. I'll get it done eventually.